Welcome everyone. My name is Guosheng He. I'm a postdoctor at EPFL in Switzerland. Today I'm going to talk about the critical parameters in dynamic store. Dynamic store refers to the phenomenon of vortex shedding and large flow separation above an unsteady airfoil when the airfoil is at a high angle of attack. The large load fluctuations associated with it can have damaging outcomes, such as the vibration or fatigue failure of the structure. The dynamic store is characterized by the formation of the primary leading edge vortex, also known as the dynamic store vortex. The goal of this study is to find the proper critical parameter that will inform us when the dynamic store is going to initiate. But first, let's have a look at my experimental setup. Okay, this is my experimental setup. I put everything back together to show you how it works. The experiment actually took place last year in a bigger wind tunnel in German Aerospace Center in Göttingen, Germany. And I use a 0015 airfoil, which is pitching around its quarter chord from the leading edge. The pitching is sinusoidal. The mean angle is the static store angle, and the oscillation amplitude is 8 degrees. I captured the flow field using two-dimensional particle image video symmetry with the plane in the middle span, and 36 pressure sensors buried inside are used to measure the surface pressure. I designed everything to be compact and portable, so I can just pack everything and do the experiment in another wind tunnel. In our experiment, we checked the pitching frequency of the airfoil. Here is the result of the dynamic store development for one of the cases. This case has a reduced pitching frequency of 0.1. On the top is the lift coefficient from the pressure measurements, and at the bottom is the flow field from the PIV measurements. At first, the flow stays attached, and the lift increases with the angle of attack. Then, flow separation moves from the trailing edge to the leading edge, followed by the formation of the dynamic store vortex. The shedding and the downstream convection of this vortex leads to full store. And then with the decrease of angle of attack, the flow starts to reattach. What is the influence of the pitching rate? First, let's have a look at the lift polars. In this plot, the black line represents the static measurements, and the colored lines are for the dynamic cases. From cool to warm colors, the pitching rates increase. If we compare the dynamic cases with the static case, we can see that the store angle happens later and the lift peak is higher. And if you will see within the dynamic cases, higher pitching rates corresponds to higher store angle and higher lift peaks. If we check the surface pressure distribution, it will tell us what is happening on the airfoil. The plot at the bottom shows the spatial temporal evolution of pressure distribution on the airfoil for the dynamic case of reduced frequency 0.1. The vertical axis is the curve length coordinates with 0 at the leading edge and the positive coordinates for the suction side. The horizontal axis is the time for one cycle. The black dashed line corresponds to the time of static store, and the red dashed line corresponds to the time for maximum lift. The plot on top is just a slice in time. We can see that the peak of the pressure coefficients on the suction side, or the leading edge suction, keeps increasing even after the static store angle. And after the maximum lift, we can see the footprint of the dynamic store vortex formation, as well as its downstream convection. Since the most significant change in pressure coefficients happens near the leading edge suction parameter has been proposed to indicate the dynamic store development. In our experiment, the leading edge suction parameter A0 is obtained by integrating the pressure distribution near the leading edge and then projected it onto the chordwise direction. The plot on the left shows the A0 values for different pitching cases in comparison with the static measurements. the maximum of A0 has been proposed by others to be the critical value to indicate dynamic store. However, as can be shown by the plot on the right, this critical value is not a constant value. It's dependent on the kinematics of the airfoil, and it is actually a function of the angle of attack when the dynamic store happens. Since dynamic store is in the end a flow separation phenomena, the adverse pressure gradient might be more relevant. That's why we turn to check the pressure gradient on the surface. This plot shows the spatial and temporal evolution of pressure gradient on the surface of the airfoil. Similar to pressure distributions, the most significant change happens near the leading edge. Note that after the maximum lift, the high concentration of adverse pressure gradient on the suction side starts to shrink and disappear. From the previous plot, we extracted the maximum adverse pressure gradient and compared all the cases in a single plot. Here are the results. On the left, for different pitching cases, before the static store angle of 20 degrees, the maximum adverse pressure gradient increases with the angle of attack, which is also in general agreement with static measurements. Interestingly, after the static store angle, all cases reach the same plateau. After that, a higher peak appears, and then the pressure gradient drops to a very low level after full store. On the right plot, we extract the values of the plateau and highest peak for different cases. Both stays fairly constant for different pitching rates. This is the critical value that we are looking for. If we look at the evolution of the maximum adverse pressure gradient with respect to convective times, we can actually check the time scale of the dynamic store development. The maximum adverse pressure gradient is now plotted against the convective times. The zero corresponds to the time instant of static store angle, and the circular dots marked the time instance of maximum A0, which indicates the beginning of dynamic store vortex formation. From this, we can say that the plateau is a precondition for dynamic store to happen, and the following peaks actually corresponds to the formation of dynamic store vortex. Another observation is that with the increasing of the pitching rate, the dynamic store development time seems to be shortened. Here, we use the time interval between 0 and the moment the pressure gradient drops to the very low level as the time scale for dynamic store development, and the result is plotted as the red line on the right. The blue line is the time scale extracted from the secondary lift peak. The results from the two methods are in good agreement. They both show a decrease of the time scale with the increase of pitching rate. Therefore, we can conclude that the kinematics of the airfoil does not change the critical value, but it does affect the time scale of the dynamic store development. Before I finish the video, I'd like to leave you with two take-home messages. First, the maximum adverse pressure gradient is a better critical parameter than the leading edge suction parameter because the maximum pressure gradient reaches the same plateau and the same peak for the same airfoil, independent of the kinematics. Second, the kinematics of the airfoil influences the dynamic store development timescale. Increasing the pitching rate will reduce the dynamic store time delay. Thank you for watching the video, and I'm happy to take questions.